This talk is called The Metaphysics of D-CTCs on the underlying assumption of Deutsch's quantum solution to the paradoxes of time travel. What I'll be arguing for today is that David Deutsch's relatively well-known solution to the grandfather paradox is actually grounded in a substantive metaphysical view that he holds, which involves the existence of parallel worlds that are distinct from those generated from the Everett interpretation of quantum mechanics. Deutsch is one of the central figures in the modern version of the Everett interpretation, and he couches his explanations about his time travel model in the language of the Everett interpretation. But I'm going to try and convince you that he actually has a different kind of multiverse in mind. Furthermore, I'll argue in the third section that it's not just a matter of interpretation. The mechanics of Deutsch's model implicitly rely on constraints on the structure of this multiverse that in no way follow from quantum mechanics itself. In short, I'll be arguing that Deutsch's quantum solutions to the paradoxes of time travel aren't really so quantum after all. There's a deep metaphysical commitment that is necessary to get the model to work the way Deutsch advertises that it does. This is potentially problematic for people working in, say, quantum information, who've taken the D-CTC model on board as their preferred model for how negative time delay would work in the context of, say, quantum computing. Quantum information folks would often prefer to avoid making deep metaphysical commitments. So the plan for this talk is, first I'll introduce the paradoxes of time travel and the D-CTC model. Then I'll look at the D-CTC model's compatibility with the Everett interpretation of quantum mechanics. I'll argue that this metaphysics of parallel worlds is an essential resource for the D-CTC model to work the way that Deutsch claims it does. And finally, I'll talk a little about an argument that David Wallace has made with respect to the D-CTC model. Okay, here's a cartoon depiction of the grandfather paradox from the Deutsch and Lockwood Scientific American article called The Quantum Physics of Time Travel from 1994. This is a standard sort of grandfather paradox story. What happens is the grandfather and the grandmother meet and fall in love and get married and have a child. And then later their granddaughter goes back in time and interferes with the grandfather and the grandmother meeting in such a way that it undermines her own existence. So if she were able to do that, that is, if she were able to go back in time and prevent her father and grandmother from getting together, how would it be possible for her to exist such that she could go back in time to prevent them from meeting? This is a classic grandfather paradox kind of case. So here's another picture from that same article. This is a simpler grandfather paradox story in which the time traveler is simply trying to prevent herself from getting in the time machine. Deutsch's answer, and this is just by way of preview, is to presuppose a model wherein roughly what happens is that there are two worlds, here called the A universes and the B universes. The time machine actually takes the time traveler into the past of another world in which her counterpart is about to get in the time machine. She can, without causing a contradiction, stop that person from traveling because she's not identical to her counterpart. What we're left with after this is all over is a collection of B universes in which there is no longer anyone present, and a collection of A universes in which there are two people present, the time traveler and her counterpart who successfully prevented her from getting in the time machine. The analog for this story with the grandfather is that the girl doesn't prevent her own birth because it's not her own grandfather whose date she ruins. It's the would-be grandfather of a would-be counterpart, so there's no contradiction. To simplify all the complex elements of that story, we can consider a simple physical system that enacts a grandfather paradox. Here is a physical system, a ball that's on a certain particular trajectory, such that it enters the future mouth of a wormhole, and the trajectory that it's on leads to interference with its original trajectory in the past. The traditional solution to this paradox, going back at least to Lewis and Nabokov, is to say that those particular trajectories are impossible. There's a global consistency condition that rules out such initial states because they lead to inconsistencies. Deutsch is uncomfortable with this because he believes it violates what he calls the autonomy principle. Here's from the Deutsch and Lockwood article. According to this principle, it's possible to create in our immediate environment any configuration of matter the laws of physics permit locally, without reference to what the rest of the universe may be doing. That is, global consistency conditions seem to interfere with what's physically possible given your local physical state. So the initial state that leads to this trajectory is ruled out as a possibility because it leads to a contradiction on the consistency condition solution. However, there are other trajectories that aren't ruled out, right? That trajectory, for example. But part of what Deutsch finds troubling is that there's nothing about the physics local to this system, that is, there's nothing about the dynamics that governs the setup of this experiment, that tells us that this initial condition is illegal. Rather, it's somehow ruled out by a global consistency condition. So here are a couple of notes to keep in mind. This kind of example is a little bit misleading for the following reason. There actually are solutions for these kinds of systems. This idea goes back, I think, to Feynman, but it was clearly and completely worked out by Tim Modlin. Since there's a continuum of possible trajectories the object could take into the future mouth of the CTC, there will be some self-consistent interaction between the object leaving the past mouth of the CTC and the older version approaching the CTC. When we look at Deutsch's model, we'll see that he's using a similar strategy. He begins by analyzing systems that can only be in classical states, analyzing classical bits, for which the paradox is a problem. He then relaxes that consideration, allowing the information-carrying systems to be in quantum states, which allows him to formulate a fixed-point solution. The larger space of quantum states plays an analogous role to the continuum of possible trajectories in the classical fixed-point solutions. Regardless of the fact that there are classical fixed-point solutions to the kinds of examples we were just looking at, Deutsch still thinks there is a conflict with the autonomy principle. So maybe what he's concerned with isn't that initial conditions are ruled out, but what is ruled out is the trajectories actually entering the CTC. Deutsch's quantum model allows for the system to be in any state, for a system in any state, to enter the future mouth of the CTC. In the remainder of the talk, I'll follow Deutsch's setup, which doesn't make reference to these classical fixed-point solutions. So Deutsch suspects that the problem with the classical solution to the grandfather paradox is that it is classical, in the sense that the state of the system entering the CTC is classical. He suspects that since quantum mechanics allows for more complicated states, like superpositions or mixed states, that might help. So he develops this framework in which he can consider the effect of allowing systems to be in quantum states. He characterizes these physical situations entirely in terms of their information flow. He thinks that considerations about space-time geometry or other natural ways to think about time travel are in fact distractions. He believes, and he doesn't really argue for this, but he believes that all that is relevant for the study of time travel effects is the information flow of the system, so he abstracts away all of the physical details aside from the flow of information. He models everything in terms of quantum computational circuits, because it's the easiest way to keep track of the evolution of the quantum information through interactions. And he allows the information-carrying systems, that is the bits, to be in quantum states. So he's considering qubits traveling through a computational circuit. Here's an image of what one of those example circuits looks like, and we'll talk in detail about what's going on here. But it's important to understand that this circuit diagram, which Deutsch uses as one of the key examples of his paper, is not what he would call fully transformed. We'll see a fully transformed version of this circuit in a few minutes. The full transformation abstracts away these topological features that are still present in this version. That is, you can see the path of the qubit traveling back through time right there where that's that loop with the -1. That's a topological feature of what the CTC looks like in space-time. But the full transformation abstracts away topological features like that, and it models the circuit entirely just in terms of the information flow. So that is to say, the CTC on this version of the diagram is modeled as a closed loop for the information carried by a single bit, and it's exactly that feature that's going to be important to pay attention to. So this is okay in this example because he's using this diagram to tell the classical story about the grandfather paradox, but part of the problem with the argument as it's presented in the paper, and as I'll argue part of the problem with Wallace's understanding of the D-CTC model, is that he relies on this partially transformed version of the circuit even when he's reasoning about the quantum mechanical case. Okay, so what makes a circuit like this classical? It has to do with the kinds of states that systems are allowed to be in. In the classical case, you only consider systems that are in the states 0 and 1. But in the quantum case, you can allow your systems to be in other kinds of quantum states. So let me explain what we're looking at here. This part of the circuit is the closed time-like curve region. It's the trajectory that doubles back on itself, obviously, and that big -1 is just to indicate that we've got a negative time delay. This is the chronology respecting region. This corresponds to that trajectory where the ball just misses the CTC altogether. Remember back to the example that I gave of the allowed trajectory in the classical case where we're considering the ball entering the future mouth of the wormhole. There was that blue ball that just missed the future mouth of the wormhole altogether, so that is a classically allowed trajectory in the presence of a CTC. So that's what this chronology respecting region represents. The rectangular box is the region of interaction. In a fully transformed circuit diagram, the interaction would be instantiated by quantum gates. Basically, this is the only place in the circuit where the states of any system can change. There's no other evolution on these channels. The way that we represent which trajectory is being followed is by having the system that's on that channel be in the state 1, which represents the presence of a ball on that trajectory, or the presence of the time traveler on the CTC, and the other system in the state 0. So these are the two allowed input states for the 2 bits that represent the physical situation we were just looking at. If we're in the first input state, that corresponds to the ball missing the CTC. Remember, the state 0 represents an empty trajectory. And if we have the second input state, that represents the ball traveling along the CTC, giving rise to the paradoxical self-interaction. That interaction is embodied in exactly what the mapping of the inputs to the outputs in the region of interaction is. In the fully transformed version of the circuit, it's a function of the gates that are present in that region. But in this example, Deutsch just tells us what that interaction is. So let's consider the simple case first. This represents the situation where the ball misses the CTC. The inputs are x equals 1, y equals 0. As the 2 input bits approach the region of interaction, you'll notice that they're not alone. The interaction is actually a function of the states of 3 systems. So the question is, what state is that system in and why? It's pretty obvious from the circuit diagram where this third system comes from. It's just the older version of the system that's about to travel around the CTC. So here's the mapping affected by the interaction. Notice that it's just adding x plus 1 to the 2 input states. Also, notice that the state of the system entering the region of interaction at z, that is the state of the system coming off the CTC, is always the opposite of the state of the system entering the region of interaction on channel x. So z just equals x plus 1. This is because the state of the system on channel y is always the opposite of the state of the system on channel x. And the state of the system at z is always the same as the state of the system at y. So we can replace our z in the interaction here with x plus 1. This interaction is just a controlled NOT gate, with z as the control and both x and y as the targets. A C-NOT gate is a standard quantum computational circuit. If z equals 0, if this whole expression is equal to 0, then we'll be adding 0 to x and 0 to y, and nothing changes for either of them. But if z equals 1, then the states of both x and y get flipped. And remember, this guy over here coming off the CTC is what we're calling z. Okay, so the first thing to consider is what happens when y and z interact, when they both enter the region of interaction. Y is 0, so let's just replace that in our expression of the interaction over here. And z, or x plus 1, is also 0, so we'll put that over here too. Then what happens is that the younger version of the system on the CTC exits the region of interaction and goes on to become z. So we can replace our z over here with 0 as well. Then the older version of the system from the CTC exits that region of interaction. Now, what happens with x? The input state for x is 1, so we'll replace that over here. And z, or x plus 1, is equal to 0. So that entails that this system passes through the region of interaction unchanged. Then both go off to be measured. Okay, let's look back at the interaction and introduce the consistency condition that's at play here. Remember, this is in the classical context. Here it is. What it says is that y plus x plus 1 must equal x plus 1. That is, the post-interaction state of y must be the same as the pre-interaction state of z. That's just because they're one in the same system, so they must be in one and the same state. Here's y plus x plus 1, and here's x plus 1. And as we know, z is just the older version of the post-interaction state of y. So this evolution satisfies the consistency condition. But now let's look at the paradoxical case, where x equals 0, meaning that that trajectory is empty, and y equals 1, meaning that the ball is going around the CTC on a trajectory that will cause an inconsistent self-interaction in the region of interaction. So they approach the region of interaction, and they're joined by the older version of the system on y. Note the fact that the state coming off the CTC at z is equal to x plus 1, just like before. Here's the interaction again, and here's a reminder of what the C0 gate does. So x and y enter the region of interaction, but because we're adding the state of z to the state of y, remember z is the control bit of the C0 and y is one of the targets, a bit flip is enacted. And likewise over here. And then they all leave the region of interaction and go off to be measured. But how do we fare with respect to the consistency condition? Remember, the post-interaction state of y is supposed to be the same as the pre-interaction state of z. But z was equal to 1. So the consistency condition is not satisfied. This means, according to the classical solution of the grandfather paradox, this initial condition, this input state of x equals 0 and y equals 1, is somehow prohibited. So the classical solution says that the input x equals 0, y equals 1 is not allowed. But Deutsch considers this to violate the autonomy principle. This also can be referred to as superdeterminism. It's something above and beyond just the simple determinism of the physical theory that's preventing this initial condition. So the D-CTC model uses the resources of quantum mechanics to find a self-consistent solution for any input state. Okay, so here is the general form of CTC circuits in the Deutsch model. Remember how I was talking earlier about how that other diagram wasn't fully transformed? That's because it still had some of the geometrical features of a physical CTC. But Deutsch's model actually requires that we abstract away from that and consider only the information flow through the circuit that looks like this. So where's the CTC? Well, notice how these two surfaces along the bottom channel are identified. That just means that when you pass the front barrier, you just go back to the identical point in the past. So time is going from left to right here. Now, I've also included two unitary gates represented here. In general, they'll look like this square one with the U in it. But the other one that I've included here is the standard notation for a gate that's really important for all these CTC circuits. It's called the swap gate. And what it does is it takes the state of the system on one channel and puts it on the system on the other channel, and vice versa. That is, it swaps the state from the top channel to the bottom channel and from the bottom channel to the top channel. So if the top channel is in the state 1 and the bottom channel is in the state 0, when they hit a swap gate, the states will swap. So then the top will be in the state 0 and the bottom will be in the state 1. You'll see how that works. Okay, so the standard form of the circuits have the following features. There's a closed loop of information located on the CTC, that is, on that channel along the bottom with this, you can see this is called row CTC, and it's got these two surfaces that are identified. That's your CTC. It's a closed loop. So there's a closed loop of information located on the CTC. Another feature is that there is no change of states in between the gates. All the evolution of the systems happens in the gates. There's no evolution outside of the region of interaction, including when a system is going along the CTC. So whatever the state is at the point before it hits the future mouth of the wormhole, that is, that identified surface to the right, whatever the state is there is going to be exactly the same as the state coming off the past surface of the CTC. That is to say, there's no change of state that happens outside of any of these unitary gates. So here is that fully transformed grandfather paradox circuit. These two things here are the standard notation for the C0 gates. So the system on the CTC, represented by this notation rho CTC here, is the control bit. And the first target is this lower channel psi2, and then the second target is the upper channel psi1. And then here is the swap gate. It takes whatever the state is on channel psi2 and swaps it onto the CTC and vice versa. So here are the same two input conditions we were considering before. First, we'll quickly go through the classically allowed evolution just to get a sense of what we're looking at in this fully transformed version of the circuit. So notice that the system on the lower channel, psi2, is the one that goes into the CTC via the swap gate. So that's like our Y, our state Y from the other diagram. So this setup condition represents the ball passing by the CTC without entering. So as they approach the region of interaction, a third system comes out of the past mouth of the CTC. Notice that in the fully transformed version of the circuit, there are actually three separate systems. There is a system that's permanently bound to the CTC, which can only interact with the chronology respecting channels via the gates. This is different from the other situation in which you had two systems, Y and Z, which were actually just two different stages of the same object, a younger version and an older version of the same ball, for example. Here there are genuinely three systems, and just as a preview, this is the feature of the fully transformed version that Deutsch relies on for his solution to the grandfather paradox, and which I think causes a problem for him later on. Okay, so let's go through all of the possibilities of what the state of the system bound to the CTC could be. First, imagine it's in state 0. Then when it hits the first C0 gate, it has no effect on the state of the system on the lower channel, and likewise for the state of the system on the upper channel. Then, when it gets to the swap, it goes like this. And then the system on the CTC goes around and comes out the back. Okay, these two systems go off to be measured. Here's the quantum mechanical version of the consistency condition that Deutsch introduced for his model. It basically says the same thing as the classical consistency condition. Rho CTC, which is the name of the state bound to the CTC, must be the same as the state of itself. You can see rho CTC is in the middle there on the other side of the equation, after being tensored with the input states. And the unitary is applied to the whole composite system. That is to say, after the effect of the region of interaction, the state of rho CTC must be the same as it was before it entered the region of interaction. That's just because it's one and the same system here at the future mouth, the future surface of the CTC, as it is here at the back surface, the past surface of the CTC. And since there's no evolution of the state of the system outside the region of interaction, it must be the same at the future surface as it is at the past surface. Now, the big difference between this and the classical version is that this allows for the system on the CTC to be in these general quantum states. Rho represents a mixed state in quantum mechanics. So the rho of the name rho CTC should be a clue that the system can be in these mixed states, and in fact it's exactly that which allows for Deutsch to find a fixed point solution for any input states. Okay, so let's reset and consider the other classically disallowed input condition to see how the quantum model can solve the paradox. So here is the classically disallowed input condition. Let's think about what we might see coming out of the past mouth of the CTC. Well, since there's a swap here, it seems like a good bet that it will be a 1, since the input state on the lower channel psi 2 there is a 1. So there's your 1. But this won't work, because as soon as we get to the first C0, we'll see that the 1 on the CTC will flip the 1 on the lower channel. And then it would be that state that gets swapped onto the CTC. And there's our contradiction right there. So it can't be a 1, but how about a 0? The first C0 will not cause a bit flip, in this case because the control system on the CTC channel is in the state 0. But this is just as bad, as it also leads to a contradiction. So far, this is just a restatement of why there's a paradox when the systems all must be in either state 0 or 1. That is to say, when we're considering the classical case. But the power of the D-CTC model is that the system on the CTC can be in any quantum state you like. So there is a fixed point solution when we allow the system bound to the CTC to be in a mixed state. And here's the particular mixed state that is going to be the solution for this circuit. That means that when the system coming off the CTC is in this mixed state, this state that's allowed by quantum mechanics, it produces a self-consistent evolution, even with the classically disallowed input states. And this fixed point is unique for this circuit. So here's how I'm going to represent the mixed state, right? If you look at the form of the mixed state here, you can see it's weighted half in the state 1 and half in the state 0. So that's why I've represented it like this. Okay, let's see what happens when it's this state that comes off of the CTC. When it interacts with the system on the lower channel, the component part of the mixture that's in the state 1 has an effect, and the component part of the mixture that's in the state 0 has no effect. So the result is that it brings the system in the lower channel into a mixed state as well. And the same thing happens with the system on the upper channel. Now, the swap does its job, and the system that ends up on the CTC is also in the correct mixed state, so there's no contradiction. And finally, these two guys go and get measured. So the solution is based on the existence of this mixed state on the CTC. The mixed state is this, and the final output state is also mixed. Right, when they go off and get measured, each of those, you can see there's a component 0, 0 means that the first qubit and the second qubit are both in the state 0, and the other component of the mixture is that the first qubit and the second qubit are both in the state 1. But what do these mixed states represent? For Deutsch, they represent a collection of worlds. Remember this picture from earlier? This is where those worlds come from. Here's the output state again, and you can see that there's a component of the mixture in which there are no people present. These are the B universes. Remember, the time traveler enters the CTC and leaves that world empty. So you can see after the time traveler enters the CTC, there's nobody remaining in that world. And there's a component of the mixture in which there are two people present. These are the A universes. These are the worlds in which the time traveler successfully stops their counterpart from entering the CTC, leaving both of them in that world. So let's look in more detail at how this is all supposed to work. Just like with the output states, Deutsch thinks of each of these components of the mixture on the CTC as existing in separate worlds. Here's what this looks like. The mixture is spread across two worlds, and in each world the input states are the same. Note that the one on the bottom is upside down. In both cases, the system that gets swapped onto the CTC is in the state 1, which is the classically paradoxical input. In both worlds, the time travelers approach the region of interaction. In the upper world, the state of the system on the CTC is a 1, so it's going to cause a bit flip for the lower channel. But in the upside down, the state of the system on the CTC is 0, so it won't cause any bit flip. So here's our mixed state spread across these two worlds. And here comes the bit flip on this channel, and nothing happens in the lower world. Then they all advance to the next gate. Again, there's a bit flip in the upper world, and again, nothing happens in the lower world. Then they hit the swaps. And now these all go off to get measured. And notice, here's your 1, 1 on the top and your 0, 0 components of that output mixture that we were looking at before. But what about the systems on the CTC? Remember, we started with a 1 in the CTC, coming off of the CTC in the upper world. Where does that come from? Well, it comes from the lower world. And likewise with the 0 on the lower world. This leaves us with the same mixed state that we started with. But how is that supposed to work? According to Deutsch's model, there is some connection between the worlds induced by the existence of the CTC. That links them up so that the information from one can travel to another. Think about the classic physical model of the CTC, a wormhole. In Deutsch's picture, the wormhole connects to another world. And it's through that connection that the information can flow in this way. So here's the upshot. Time travel takes place across multiple universes. CTCs connect up these separate universes. This solves the grandfather paradox since Alice is not interfering with her own past, but with a counterpart's. Here are some quotations where Deutsch says just that. This is from the original 1991 paper. The key thing to bear in mind when trying to visualize it is that in half the universes, let's call them A universes, the encounter happens, and in the other half, the B universes, it does not happen. In the A universes, an observer appears from nowhere, no one having embarked on a chronology-violating trajectory in that universe, and in B universes, an observer enters and disappears into nowhere, since no one has emerged from the chronology-violating trajectory in that universe. But of course, it's not really from nowhere and into nowhere, but from and into other universes. And this is from the Deutsch and Lockwood Scientific American article. If the classical spacetime contains CTCs, then according to quantum mechanics, the universes of the multiverse must be linked up in an unusual way. Instead of having many disjoint parallel universes, each containing CTCs, we have, in effect, a single convoluted spacetime consisting of many connected universes. The links force the time traveler to travel to a universe that is identical up to the instant of her arrival with the one she left, but is thereafter different because of her presence. But I want to point something out. Deutsch constantly advertises this solution as something that follows directly from quantum mechanics, or at the very least the Everett interpretation. See here. I'm going to argue that this isn't the case at all. The worlds Deutsch is relying on for this model are not the worlds of the Everett interpretation. But a big part of the reason why this isn't clear to people is that he uses the same term to refer to both. Deutsch is one of the only Everett advocates, at least among the ones I'm aware of, who seriously uses the term multiverse when talking about the Everett interpretation. And just a final note, we can see why these worlds can't be from the Everett interpretation right here in this quotation. The worlds must be identical up until the time that the CTC comes into existence for Deutsch's model to work, but there are no such worlds in the Everett interpretation. I'll turn to that argument now. Is Deutsch relying on the many worlds of the Everett interpretation to solve the paradoxes of time travel? So I'll give just a really brief intro to the Everett interpretation here so that we can answer this question. Everett is an interpretation of quantum mechanics. That is, it's a way of saying what quantum mechanics is actually about. It's a way of making sense of how quantum mechanics can be true. It's a so-called many worlds interpretation, meaning that it makes sense of the superposition of the quantum state of the universe without the need for a collapse. The Everett worlds are those worlds that are consistent with the evolution of the universal wave function. That is, quantum mechanics tells us what worlds arise and how they are related. It's not as permissive as, say, Lewis's modal realism, which says that worlds are the result of recombination. The Everett worlds are the result of the dynamical evolution of the wave function of the universe. These are important features of the Everett interpretation for my argument, but let me spend a little bit of time to give a more general introduction to what the Everett interpretation is all about and why we might believe it. Everett is a solution to the measurement problem of quantum mechanics. This is a fundamental problem of quantum mechanics from the perspective of philosophers of physics. So let's look at what that is and why it's a problem. There are a few ways to talk about this. One way to understand the measurement problem is that it's a problem for the consistency of quantum theory. It's also often talked about in terms of the interpretation of quantum theory, in the sense that a proper interpretation would solve the measurement problem. But I think it's best understood as a problem about the fundamental ontology of quantum theory. This is, of course, related to interpretation. What I'll do on this next slide is give you a sketch of the axioms of quantum mechanics and show how you can understand the measurement problem to be a problem with the consistency of these axioms. So here's one really kind of quick and dirty way of talking about how quantum mechanics is structured. Systems are represented mathematically by wave functions. Observables are represented mathematically by things called operators. Now, the wave function is the evolution of the wave function is described by a particular deterministic equation of motion called the Schrödinger equation. Now, it's also true in quantum mechanics that a system that's in a particular state psi will have a certain probability of a given outcome A when the measurement A is performed. Subsequently, the system will be in the state corresponding to that outcome. Now, it's these two axioms that are in contradiction with one another. So here are some slightly simpler ways of saying the same two things. All systems evolve in time according to the Schrödinger equation, which is the dynamical law for quantum states, except when a measurement is made. In that case, the evolution of the system is described by a probabilistic law, and the system discontinuously jumps into a new state. Quantum mechanics, or the Schrödinger equation that is, says that systems can evolve into superpositions, which means that their state is not a definite state of a particular observable, rather it's some kind of combination of two mutually incompatible states. There are a few different things being superposed in this example here. One is the position of the system, right? You've got the system that follows a trajectory along the top of the slide and follows a trajectory along the bottom of the slide. Another is the color, obviously, and the last is the shape. Remember, there's only one system being represented here, but what this is meant to depict is that the state of that system is somehow a combination of having traveled along the top path, turned blue, and kept the same shape, and having traveled along the bottom path, turned red, and grew some extra arms. So this is how the Schrödinger equation says quantum systems can evolve in time. But quantum mechanics also tells us that when the system is observed, only one of those outcomes is registered in the measuring device, here represented by the eyes of the observer, but that's not meant to represent the idea that a person is necessary for this effect. Somehow the measurement changes the state of the system. This is called the collapse of the wave function in standard quantum mechanics. But the problem is that quantum mechanics itself doesn't define what constitutes a measurement. In textbook quantum mechanics, you treat the system under consideration as being quantum mechanical. And you consider there to be a strict distinction between the part of the system you treat quantum mechanically and the measuring device, which you treat classically. That is, it's always in definite states and doesn't evolve according to the dynamical laws of quantum mechanics. That is, quantum mechanics itself doesn't tell you about this split between the quantum world and the classical world. Now, the problem can be understood in the following kind of way. I can introduce another observer and treat them as being the classical measuring device. And they're allowed, according to quantum mechanics, to treat the entirety of this system as quantum mechanical. Quantum mechanics itself does not tell you where the separation between the measuring apparatus and the system that's being treated quantum mechanically is. So, if we treat the first observer here as a part of the quantum system, what happens? Well, the interaction with the superposed system sends the observer into a superposition. And then we just run the same argument here with this outside observer, who we're treating as being classical. It's the interaction of that observer with the quantum system that collapses the wave function down into a single outcome. So, to summarize, there's no distinction between the classical and the quantum built into quantum mechanics. That red line isn't a part of the theory. All systems, including systems partly constituted by other observers, can be treated quantum mechanically. There is no definition of a measurement formulable in the theory, and this is why it's referred to as the measurement problem. So, since quantum mechanics says that the Schrödinger equation, that is the equation of evolution of a physical system, applies to all systems, it implies that experiments don't have definite outcomes. And this is in conflict with what we see. We don't see macroscopic systems in superpositions. So again, here are the three sort of ways that I characterized the measurement problem before. To talk about it in terms of consistency, you would say, well, when you look at that set of axioms that I laid out before, there's no rule about when one or the other of the two dynamical laws applies. So this can be solved by means of an interpretation. If we can figure out a consistent way to understand how quantum mechanics applies to the real world, that would necessarily include a solution to the measurement problem. But the way I like to think about it the best is in terms of ontology. That is, if we were to be able to settle what the fundamental stuff of the world is, then that would, constitute a good interpretation. It would tell us how to solve the measurement problem. Now, that way of talking about it seems to imply that quantum mechanics itself isn't the complete story. It will be, the quantum formalism plus some ontology, or possibly, a slightly altered version of quantum mechanics. So, I'm going to introduce a few interpretations here to give you a sense of how it is, talking about ontology can help solve the measurement problem. And then this is all by way of talking about why we might prefer the Everett interpretation. So in terms of theories that posit a particular ontology that then go on to solve the measurement problem, we've got Bohm's theory, or sometimes called Bohmian mechanics. It tells us explicitly what the ontology of the world is. The world is made of particles, and there are also waves. Physical systems, on this view, always have definite properties, so you don't get these superpositions. The superpositions are features of the wave function. They're not features of the physical systems which are constituted by particles. Okay, another alternative approach to solving the measurement problem is called the GRW theory. This is a little bit more complicated. It's essentially an ontology of waves, and it has a feature of the theory itself that determines the split between the quantum and the classical. So this is a different kind of solution to the measurement problem. That is to say, the theory itself tells you when you treat something as quantum mechanical and when you treat it as classical. And the third interpretation we'll look at is the Everett interpretation. This is an interpretation of quantum mechanics where it takes the formalism seriously. It looks just at the bare formalism of quantum mechanics and is guided in its ontological commitments from that. So the wave function of the universe, which is a quantum mechanical device, it's something that exists in the formalism of quantum mechanics, the wave function is taken to represent the basic ontology of the world. Now the way that they solve the measurement problem is by saying that there is no outside observer. So everything is superposed. That is, every physical system is, these superpositions persist through these observation events. Now that might not sound like a solution to the measurement problem, but I'll explain why why it works. Okay, so first let's look at Bohm's theory. Now on Bohm's theory, like I said, the particles that constitute the physical systems are never themselves in a superposition. So that is to say, there's always one definite state of the system. So when the observer interacts with the physical system in that state, that's why they see that one particular measurement outcome. Right? There's no superposition of the system being sort of in the blue state and sort of in the red state. It's just always in the blue state. Okay, let's look at GRW theory. GRW says that for microscopic, that is, for small systems, you do still get these superpositions. But when you interact with a system that's large enough, and this is like in terms of size, basically, in terms of number of particles that constitute the physical system, it defines a scale at which it's appropriate to apply this classical quantum divide. So once it's larger than a certain size, that is, so like the observer here, the measuring apparatus, is larger than a certain size, it causes a physical collapse of the wave function to be in some one definite state. So the interaction between the system that's being observed and the observer causes there to be a single outcome, a single definite state. Okay, so how does the Everett interpretation work? Well, you start with your physical system. It goes into a superposition. And remember I said if you treat the observer quantum mechanically, that will entail that the interaction between the physical system that's being observed and the observer causes the observer to go into a superposition. Remember the way that we solved this before was by introducing an outside observer. But there's no divide between what's treated quantum mechanically and what's treated classically on the Everett interpretation. So the outside observer themselves will, when they interact with the physical system, when they observe the state of the physical system, go into a superposition. Now, this doesn't seem obviously like it's a solution to the measurement problem, but one thing that you'll notice is that the component of the green-eyed observer that saw the red star is part of the same story, essentially, as the purple-eyed observer who saw the red star. They only see one another. There's no physical interaction between the green-eyed observer who sees the red star and the blue star, right? In that branch of the wave function, in that branch of the superposition where the system evolved into the red state, the purple-eyed observer saw red and the green-eyed observer saw red. And likewise for the component of the superposition where it evolved into the blue state. So there are these self-consistent stories about what's observed. And the Everett interpretation essentially just says that this goes on all the way up to the scale of the entire universe. So there are these multiple different consistent stories about what's observed by a given observer. So if you ask one of the green-eyed observers all the way at the top on the right-hand side what they saw, they will answer red for every one of these quantum events. So that is a very rough characterization of how the Everett interpretation is a solution to the measurement problem. It denies that there are actually unique outcomes to particular experiments, but it can tell a story about why it seems to any given observer like they're in a world in which there are outcomes to experiments. Okay, so the question is Deutsch relying on the many worlds of the Everett interpretation to solve the paradoxes of time travel? I'm going to argue that he isn't. And it's a two-part argument, considering the ways in which you might be able to travel to an identical world in this Everett structure of many worlds. Remember, Deutsch's model relies on the fact that the world that the time traveler travels to is identical to their world up until the point when they arrive there. So I'm going to suggest that the Everett interpretation, this branching structure of the Everett interpretation, doesn't support that. There are no identical worlds to the world from which the time traveler left. Okay, so like I said, it's a two-part argument. So I'm going to consider two ways in which you might try and find such an identical world. The first is that you travel into your own past, right? You travel into a previous, a branch that is part of your own actual history. So this would be you traveling to a world that's identical to your own up until the time travel event, but there's a problem here. Okay, the second option is that you travel to a separate branch from the one in which you live, and this is more in line with the whole traveling into a parallel world thing that Deutsch describes. But this too has problems. So let's think about possibility A first. Imagine you travel back into the past of your own branch. You land here at the star. Well, that would change the quantum state of the universe at that point in your past, which would erase the branching future that had happened, including potentially eliminating the very branch from which you came. And this would lead to a new branching history. That is, the quantum state at A is different from what it was before. And given that the quantum state determines the branching structure, that would mean that you're undermining your own history. So where did you come from? This proposal is actually just another version of the grandfather paradox. You can't change your own past. This is why Deutsch adopts the transworld model in the first place. So what about the second possibility? The possibility where you travel to a nearby branch. Well, let's say you land here. The last point at which this history, this branch, was identical to your own history was the point at which they branched apart. So there is some part of the history of this world that's different from the history of the world from which you came. You know, you chose a blue car and your counterpart here in this world chose the red car. But it's an important part of Deutsch's model that the world you come from must be identical to the one you leave. Otherwise, he wouldn't be able to guarantee that the mixed state is acting on the same input conditions in both worlds. Here's a quotation that we've seen before. A universe that is identical up to the instant of her arrival with the one she left, but is thereafter different because of her presence. But on this model, where you're traveling into another branch of the Everett structure, the world you're landing in is not identical to the world from which you left. Otherwise, it wouldn't exist. So here's the problem. Here's the dilemma for interpreting Deutsch's model in the context of the Everett interpretation. Path A leads Alice to a world that was identical to her own up until her arrival, but it undermines the existence of her own branch, and this is a grandfather paradox. Path B doesn't suffer from a grandfather paradox. It sounds more like what we know Deutsch is trying to achieve by saying that you are interacting with a counterpart of yourself, but it leads Alice to a world that's distinct from the one she left. So the solution for Deutsch is to rely on a structure of parallel worlds. That is, worlds that are not the result of the Everett branching structure. There exist among these parallel worlds ones that are identical to the worlds in our branching Everett structure. This doesn't do away with the normal Everett picture, but it supplements it with an additional ontology. And if you go from your original world to one of these separate identical parallel worlds, then you're okay. So The D-CTC model needs to be embedded in a structure of parallel worlds, and these are what is represented by the mixed state on the CTC. The mixed state does not result from the Schrödinger evolution of the quantum state of the circuit plus the input conditions. Therefore, it is uncaused. It's part of a closed causal loop. This last point is really important. The state of the system on the CTC is uncaused. It has no dynamical antecedent. It simply is in the state that it's in. Now, keep that in mind because it's going to be important in a moment. So, after working on this project for a long time, I became aware of the fact that David Wallace has made a similar point in his book. So here's the passage that suggests the idea about parallel worlds going beyond the Everett interpretation. Wallace says, conversely, the multiplicity present in a mixed state is, as we have seen previously, of a rather different kind from conventional Everettian multiplicity. The parallel universes of the Everett interpretation are present even in pure states, are emergent phenomena whose concrete form is given by decoherence theory and affect one another dynamically via interference. The multiple universes, actually multiple entities which are themselves multiplicities of quasi-classical branches, in mixed states are present by interpretive fiat. All we have managed to establish, and all Deutsch establishes, is that accepting parallel universes can solve time travel's contradiction paradoxes. There is nothing inherently quantum mechanical about this observation, and it would be reasonable to regard the quantum and time travel parallel universes as being of an entirely different kind. And there's some further circumstantial evidence that some other philosophers were tuned into this feature of Deutsch's view. These passages are from the Arnsenius and Maudlin Stanford Encyclopedia of Philosophy entry on time travel and modern physics. They say, Deutsch instead recommends the following many worlds picture of mixtures. And they also say, now whatever one thinks of the merits of many worlds interpretations, and of this understanding of it applied to mixtures. So my claim here is that they likely would have said Everettian, or the many worlds interpretation, rather than many worlds interpretations, which is a more kind of general title. So this seems like evidence that they were probably aware of the fact that Deutsch's many worlds for the D-CTC model are not identical to the many worlds of the Everett interpretation. In any case, so now I'm going to talk a little bit about why I think that, aside from the two examples I just gave, it's not more widely recognized that the multiverse that Deutsch is talking about is not the Everett multiverse. So Deutsch himself often talks about the Everett interpretation in terms of parallelism. He also uses the term multiverse for the many worlds of the Everett interpretation. And I call this the many worlds multiverse. So I'm going to draw a distinction here between the multiverse as it exists in the Everett interpretation and his notion of the multiverse that he's relying on. So the D-CTC model relies on worlds that are genuinely parallel, right? That aren't a feature of this, they aren't resultant from this branching. They're genuinely parallel. And this is based on the existence of the mixed states. So he uses the term multiverse for these worlds as well, and I call these the mixed state multiverse. So we've got this distinction between the many worlds multiverse, that is the Everett multiverse, and the mixed state multiverse, the Deutsch multiverse. So here's some evidence that he's using this multiverse terminology in an ambiguous way. He says, for example, according to Everett, if something physically can happen, it does in some universe. Physical reality consists of a collection of universes, sometimes called a multiverse. And here in this example, Deutsch is describing the Everett interpretation in terms of parallelism, but here saying that you need to understand that as an approximation. He says, the idea that quantum theory is a true description of physical reality led Everett and many subsequent investigators to explain quantum mechanical phenomena in terms of the simultaneous existence of parallel universes or histories. Note, he's saying that Everett explained quantum mechanics in terms of the simultaneous existence of parallel universes. And he goes on to say, however, if reality, which in this context is called the multiverse, is indeed literally quantum mechanical, it must have a great deal more structure than merely a collection of entities each resembling the universe of classical physics. Since quantum mechanical interactions are local, it must in the first instant be local physical systems, such as qubits, measuring instruments and observers that are split into multiple copies. And this multiplicity must propagate across the multiverse at subluminal speeds. That is to say, he's saying if the Everett interpretation of quantum mechanics is right, you can't think of these as merely parallel classical universes. You need to think of these as branching universes. They split into multiple copies, and that's mediated by physical interactions. That's why it needs to go at subluminal speeds. And now finally, here's a little bit more textual evidence from the original Deutsch paper on D-CTCs that suggests that he has a bigger multiverse than Everett's in mind. This is sort of an oblique reference that he makes to the kinds of parallelism I've described. He discusses what the universe needs to be like to allow a pure state to evolve into a mixed state. And he says that a mixed state needs to be present at the beginning of the universe in order for this to happen. Instead of a universal wave function psi, we have a universal density matrix rho. So he's not explicitly describing the assumptions of his view. What he's talking about is what would need to be true in order for it to be possible for a system that's in a pure state to evolve into a mixed state. He says, rho of t therefore describes a collection of universes, each one consisting of multiple universes under the Everett interpretation. That is, it's a larger structure of multiple Everett branching structure, one for each non-zero probability. Each evolves precisely as if the others were absent, and it had a pure state psi of t. That is to say, each of these parallel worlds evolves just like the Everett interpretation says the whole universe evolves. This is quite unlike the Everett multivaluedness caused by a linear superposition of components of a state vector, which is detectable through interference phenomena. So that is to say, this structure of parallel Everett universes isn't describable by a single quantum, pure quantum state. He goes on to say, what is needed to express such arguments in the framework of a theory of a multiverse sometimes it has to be a bigger multiverse than Everett's. Okay, so now I'm going to move on to part 3. I'm going to try and argue here that these parallel universes actually play a really important role in the function of this D-CTC model. So you might, at this point, be asking, okay, so you've told me that Deutsch's model relies on this parallelism that isn't from the Everett interpretation, but so what? Does this matter? I argue that yes, it does. Many researchers working with the D-CTC model employ the quantum information approach. That is, they're, participating in the quantum information research program. And in quantum information, they tend to interpret quantum mechanics operationally. So the question is it possible to adopt just the operational features of the D-CTC model without worrying about this metaphysics of parallel worlds? I argue no. I argue that the explanation from the existence of identical worlds is invoked right from the beginning to get the model to work. And in what follows, I'm going to show you an example of a prediction that the D-CTC model makes that does not follow from its operationally interpretable structures alone. So the D-CTC model, without this metaphysical commitment to the existence of the structure of parallel worlds, is really just this standard circuit form and the consistency condition. That's all the technical machinery of the model. So I'm going to present an evolution that's consistent with these features, but is otherwise problematic. So this is an alternative evolution for the classically allowed input, 1, 0. This is the one that doesn't cause any problems for us with the grandfather paradox. Okay, so remember, the first thing we ask about is what comes off of the CTC. The answer that saved the day for the classically disallowed input state 0, 1 was the particular mixed state that we talked about before. But remember, there's no story about what the cause of that mixed state was. In fact, it's entirely uncaused. It has no causal antecedents. Think back to the original semi-transformed circuit diagram we were working with. Would the existence of a mixed state coming off the CTC be consistent with the way we were talking about the grandfather paradox when we were looking at this example? Well, it doesn't seem like it. It fails to be true in this solution that y plus x plus 1 equals x plus 1. That is, it fails to be true that the state of z is just the opposite of the state of x. Remember, this is why we were justified in replacing z with x plus 1, the expression of the interaction. And it's certainly not just equal to the state of y. What stops being true in the fully transformed version of the circuit is the idea that there is some causal connection between the input state of x and the state coming off the CTC at z. The only way the consistency condition is satisfied is if the post-interaction state of y and the pre-interaction state of z are both that mixed state. But in order for this to happen, the mixed state must exist on the CTC without any relation to what is chosen as the input of x. That is, the classical setup for the grandfather paradox circuit relied on the state of the system coming off the CTC being the opposite of the state of the system on channel x. That's why we replaced z with x plus 1. But Deutsch's solution to the paradox does not respect this condition. Since the state of the system at z is uncaused, there is not necessarily any relation to the state of the system on channel x. Okay, so the state of the system bound to the CTC in the fully transformed circuit is not required to be equal to x plus 1. This is necessary to allow for the existence of the mixed state that solves the grandfather paradox, but the state of z is uncaused, and therefore it's not related to the state on channel x. So consider the following evolution. We start with the classically allowed input state 1, 0. But what comes off the CTC is a system in the state 1. Since the state on the CTC is causally independent of the input state of the upper channel, this is allowed. Then the 1 causes a bit flip on the lower channel, and then it causes a bit flip on the upper channel. Then the two 1s swap, and this is your final state. Note that the state of the system coming off the CTC was the same as the state when it enters the future mouth of the CTC. That is, this evolution is totally in accord with the consistency condition. But this evolution is basically uninterpretable. What it represents is a situation where the worlds matched up by the CTC were not identical. There was not a time traveler in our world. The input was 1, 0. But there was someone getting on the CTC from another world. And the final state is chaos because of that. So the consistency condition is satisfied, but the evolution is uninterpretable. Nothing about the model itself rules this evolution out. Deutsch, however, offers the following kind of explanation for why this sort of physical evolution shouldn't be allowed. He says, if I am not going to use my time machine, come what may, then no time-traveling version of me must appear in my world. That is, no universes in which versions of me do use a time machine can become connected to my universe. If I am definitely going to use the time machine, then my universe must become connected to another universe in which I also definitely use it. And if I'm going to try to enact a paradox, then, as we have seen, my universe must become connected to another one in which a copy of me has the same intention as I do, but by carrying out that intention ends up behaving differently from me. So that's not a very good explanation. That's not a very good rule for prohibiting the kind of evolution that I just suggested. So as what I'm saying here, the conclusion of this portion of the argument is that the model alone, the operationally interpretable portion of the D-CTC model, that is, the D-CTC model without this kind of metaphysical commitment to the existence of these other parallel worlds, that model alone does not have the resources to fix the state of Z in cases where there's not a unique fixed point solution. The only explanation Deutsch offers to rule out this situation appeals to the existence of these parallel worlds and to the structure of the connections between them. And so a purely operational understanding of the D-CTC model will lead to bad predictions in certain cases. The D-CTC model is interesting and fruitful, but it's not a purely quantum solution to the paradoxes of time travel. It carries with it additional metaphysical posits that some might find distasteful. And I think Deutsch misrepresents this fact about the D-CTC model. For example, here's another quotation. He says, "What then does quantum mechanics, by Everett's interpretation, say about time travel paradoxes?" Well, the grandfather paradox, for one, does not arise. If the classical spacetime contains CTCs, then, according to quantum mechanics, the universes of the multiverse must be linked up in an unusual way. But as I've suggested, it's not quantum mechanics that dictates that. It's this additional commitment that he brings along. Here's another quotation. "So for time travel to be physically possible, it is necessary for there to be a multiverse. And it is necessary that the physical laws governing the multiverse must be such that in the presence of a time machine and potential time travelers, the universes become interconnected in the way I have described and not in any other way." But that's the totality of the argument he makes in favor of this condition that, plays a significant role for him. Okay, so briefly, to end, I want to just move on to the rest of the discussion that David Wallace has of the D-CTCs in his book. So we saw a quotation from him a little bit earlier where I said that he was agreeing with me about this structure of parallel universes that Deutsch relies on. But Wallace argues that the mixed state multiverse is the inevitable result of any model that would allow for quantum systems to travel along CTCs. That is, he points out first that it's not identical to the Everett branching structure. It's not the MWM, it's not the many worlds multiverse. But then he goes on to say, but hang on, that's not a problem, because if you have any model where you allow for quantum systems to travel along CTCs, you're going to end up with the mixed state multiverse. So in a sense, he's defending Deutsch's position. Now his argument is very simple, but it's based on a mistake. So Wallace agrees with Deutsch that a mixed state on the CTC entails the mixed state multiverse, as I just said. That is to say, if you've got a mixed state and you allow it to travel along a CTC, then you're going to have to be in a world where the mixed state multiverse. He argues that any realistic model of time travel for quantum systems must allow mixed states to travel on the CTC. He says, consider a quantum system that's entangled to any degree with the environment. That quantum system is describable only by a mixed state, quantum mechanics. It is in some mixed state. And he says, now either your CTC model forbids such a state from traveling through time, which is absurd, or it allows for mixed states on the CTC. So imagine you have your system, and you have some second system. This can be just some particle in the environment with which your system has interacted in the past. So there's some amount of entanglement between the two. It doesn't need to be maximal. It can just be some small amount of entanglement. So this one's just a little bit blue, and that one's just a little bit red. But nonetheless, they are entangled, which means their reduced states need to be expressed by a density matrix, rho. Okay, so the reduced states aren't pure. So what Wallace says is this: consider what happens when that system goes around a CTC. Wallace says that this is a clear example of a mixed state traveling around a CTC. And remember, since he agrees with Deutsch that the presence of a mixed state on a CTC entails this mixed state multiverse, he argues that this satisfies the antecedent, which entails that the world is structured in this MSM kind of way. In fact, he says, there's nothing particularly special about my example. Essentially, any situation in which part, but not all, of an entangled system undergoes time travel will require mixed states to satisfy the consistency condition. So either one, in the presence of a closed time-like curve, the universe can be in a genuinely mixed state, or two, entangled states cannot travel on closed time-like curves. But let's think about exactly what's happening in this example. Take a look at the physical situation that Deutsch describes. A system is in some state, in this case it's entangled with its environment, and that system travels around the CTC. But look again. is there any closed loop for information? This is just a single system traveling around CTC. There isn't any self-interaction in this example. Remember, Deutsch's CTC model is about information flow. It's a way of modeling the puzzling features of closed loops of information. Deutsch's CTC model models the information flow in cases of chronology violation. Physical features of the CTC are abstracted away, and what is modeled is the closed loop of information. There is no closed loop here, because there's no self-interaction. So how would Deutsch model a physical situation like the one Wallace describes? Here's the system going around the CTC again. Luckily, Deutsch tells us. He says, chronology violation in itself, i.e. the existence of negative delays, makes no fundamental difference to the behavior of a network unless there is a closed path for information. If a network has no closed path for information, there is always a denotationally trivial transformation that removes all negative delays by introducing positive delays elsewhere. If the network does have such a path, then there is always a denotationally trivial transformation that makes all negative delays occur on closed trajectory of carriers. So here's the relevant part for us. If a network has no closed path for information, there's always a denotationally trivial transformation that removes all negative delays by introducing positive delays elsewhere. Since there's no closed path for information in Wallace's example, the way Deutsch would model it would not include a CTC at all. So denotationally trivial transformations are another component of Deutsch's argument. Since all he's interested in modeling is information flow, all that matters is the function that maps the inputs to the outputs, that is the information that's carried by the qubits at the input of the region of interaction and then what the outputs look like. So he says any two circuits that implement the same function are denotationally equivalent. You can freely transform, you're just diagramming these circuits after all. You can freely transform between any of the equivalence class without altering the information flow. So this is why he introduced that standard form at the beginning, just for the ease of analysis. So the idea is that since the flow of information through the circuit is all that's relevant, you can draw a black box around the region of interaction and analyze the circuit just in terms of the mapping of the inputs to the outputs. The idea of a denotationally trivial transformation is just that you can replace the circuit with any other that has the same information flow properties. For example, here's the original version of the grandfather paradox circuit. So let's look again at Wallace's example in light of what Deutsch said. He said, anytime there's no closed loop of information, which there isn't here, you can, via a denotationally trivial transformation, eliminate the CTC entirely from the model. That means for any circuit that represents a physical evolution, like this, you can put a black box around it and analyze it just in terms of the mapping from the input to the output. And any other black box that makes the same mapping of input to output will be an equally good representation of the same physical situation. That means that inside of this black box, which takes this input to this output, notice that the output is unchanged, is exactly the same as the circuit behind this black box, which is just a positive time delay. So, Wallace's defense, the example that Wallace uses, does not count as a mixed state on the CTC, because Deutsch wouldn't even represent that circuit as including a CTC. The CTCs that Deutsch is concerned with are not the physical CTCs, right? So Wallace is talking about, imagine if you had this quantum system and you sent it through a wormhole and it went to the past. Doesn't that constitute a system in a mixed state traveling along a CTC? Well, according to Deutsch, no. What he's talking about isn't these physical CTCs, he's talking about closed loops of information. The CTCs that are relevant for the application of the consistency condition are the ones that are present on that fully transformed circuit. Remember, he said all the special properties of chronology violating networks are consequences of consistency conditions around those closed trajectories. And that's what's relevant here, is that in the Wallace example, there is no closed loop of information. Okay, so in conclusion, there's a lot of confusion about exactly what Deutsch is arguing for in the D-CTC model, even among his defenders. Part of this is because the language Deutsch uses when he's talking about the many worlds multiverse and the mixed state multiverse is ambiguous. But I've argued here today that he presupposes a substantive metaphysical picture and that this commitment is essential to the proper workings of the model. It cannot be eliminated. Thank you very much.